So allow me to share my screen. Okay. So we are now on EMA 102, Module 1, Integration Concepts and Formulas. These are fundamentals of integration. And for this slide, we start with the review. Actually, the review of what you have learned in your differential calculus. Okay, so let's start. Please let me know if my slides are not transitioning because at times my laptop is not working. Okay, so let's have a short review. Okay, you could see in your screen activity for EMA 101. So that's your differential calculus and it's a review. And it's a given that you should know this already. Can you find the second derivative of 3x cubed plus 2 over x? I will call Sam after 3 minutes.
Miss, excuse me, Miss.
Yes.
Can I ask if are we already in slide 2, Miss?
You should be seeing activity. Let's
Okay, ano, Miss? We are still in slide 1. I think it is stuck.
so it's not transitioning. Thank you. So we'll just use this one. Anyway, so you'll be seeing the answers already. Now, so that's it. Can you see my slide?
Yes, Miss.
Okay, so if you find the second derivative of 3x cubed plus 2 over x, that will require you to get the first derivative first. Can you tell me what's the first derivative for this? Or can you please solve the first derivative for this? Because what you have there encircled is the second derivative already. So what's the first derivative for this? Okay. What's the first derivative? So that would be f of x prime. This would be, okay, let me call somebody. Arabella. Are you there, Arabella?
Yes, Miss.
Okay, what's the first derivative of 3x cubed plus 2 over x? Can you dictate?
9x squared minus 2 over x squared, Miss.
Very good. Okay, so that's the first derivative. Thank you for that. So the second derivative will be the one that is encircled already there. You take the derivative of the first derivative, that would be the second derivative. So you have 18x. Now this is x raised to negative 2. So that would make this positive. So that would be positive. 2 times 2, so that would be 4. And this would be negative 2 minus 1. So that would be x raised to negative 3. Okay, now we go to number 2. Okay, somebody wrote in the chat box. Okay, thank you for that, Keisha. Thank you. Okay, I will call names so that I know that you are there. So if you're not there, I'll remove you from the room. Okay, that's, I think, fair enough for everybody. Now, you are to determine the first derivative of y here being equal to 3 square root of x minus 5 raised to 8. So if you take the first derivative of that, that would be y prime. So if you use power rule, sige, if you use power rule and chain rule together, can you dictate to me how will the derivation process proceed? Denzel, the axis, Denzel, the axis, are you there?
Miss.
Okay, can you please tell me how will we perform the differentiation here? You will use power rule with chain rule. What would be the answer? Y prime is? This is already the final answer here, but the question is, how did this came about? So Denzel, can you tell us? What should I write here? Denzel?
Dapat ko, Miss.
Oh, Who is your differential calculus? Who's your teacher in differential calculus, Denzel? Are you there, Denzel?
Yes, ma'am.
Who's your teacher in differential calculus? You forgot your teacher in differential calculus? Who's your teacher in differential calculus?
Miss Mary and Miss.
Miss Mary Ann Pandan, Dr. Pandan?
Yes, Miss.
Oh, so I will tell Dr. Pandan that you forget the very basic chain rule. Because this is basic. If you cannot remember this and you will just simply tell me that you forgot, you will have a lot of trouble here. I'm telling you already. So Denzel, review because you need your differential calculus here in integration. If you cannot process the derivative of this, you will have a hard time here in integral calculus. Okay? Now, can I have another one? Cinder, James, Kanyet. What will happen if you take the derivative of this?
Lipat mo ako, miss.
Okay, so I will remember your names. Kanyet. How can you forget derivation? It's very simple. What will happen to you in this subject if you have forgotten this one? This is even a lot easier, 5 times easier than integration. Oh, Kanyete to ha, and then Denzel the Asis. Let's see another one. Jesbert Halandoni. Jesbert Halandoni. Are you there?
Yes, miss.
Can you tell us how did this answer came about here?
Chain rule.
Or simply derive this one. Or give me the derivative of this. How will you process the derivative? Or how will you go about differentiation? So I have already 3 students who doesn't know how to differentiate. And you are here. What will happen to you in my class? John Paul Ruiz. John Paul Ruiz. Are you there, John Paul Ruiz? Are you there? Can you tell us how did the answer came about? John Paul Ruiz. Okay. I want to save time because I cannot finish the topic if we will be stuck in this particular slide, but you review your differential calculus. Okay? It's a no-no for a student who is already in integral calculus if he doesn't know how to differentiate. You're most likely not to make it in the subject if you do not know how to differentiate because it's supposed to be a prerequisite of the subject. What's a prerequisite? What does it imply? That you know it already before you take the next subject. Now, if you don't know it, I find it hard to believe that you have forgotten it. Maybe you don't really know it. Because this one is very basic in differential calculus. So please review because if you do not know how to differentiate, more likely you won't know how to integrate because it's needed here in integral calculus. If you use chain rule for y equal to the quantity 3 square root of x minus 5 raised to 8, you use power rule first to this expression. So you will have an 8. You copy the original function and you subtract 1 from the original exponent, so that would be 7. And since it's a chain rule, you need to take the derivative of what is written inside. What we have inside is 3 square root of x. What's the derivative of 3 square root of x? That would be the 3 times, you use power rule for x raised to 1/2. Because your square root of x is x raised to 1/2. So that would be 1/2 x raised to negative 1/2. Why do we have x raised to negative 1/2? Because if you use power rule, for x raised to 1/2, you subtract 1 from its exponent, that would be negative 1/2. 1/2 minus 1 is negative 1/2. So look, if we're going to process it, this 1/2 will cancel the 8 here, leaving it with the 4. So this 4 and this 3 will be multiplied. That makes it 12. And you copy that expression 3 square root of x minus 5 raised to 7. And this x raised to negative 1/2 is 1 over the square root of x. So this is your answer now. But this is not important to me. I never give a quiz, or not all my exams are multiple choice. Most of my quiz, if not all, are open-ended, meaning I require my students to show their solution. So if you do not show your solution to me, more likely you won't get any mark. You will not earn any mark on anything. So please understand when we discuss things here, and let me know if there's something that you cannot follow. If that thing that you have in question is something in my understanding should be learned previous semester, I will not anymore go through the detail of discussing it. Why? Because it should have been learned the previous semester. If it's something that is related to what we're discussing, then I will explain it again, as long as time permits me. Okay? Now, any question with number 2? Okay, John, Oxenio, what's the question?
Miss, for the final answer, is it okay to further simplify?
This is already simplified. Or if you want to rationalize the denominator, you can multiply this one by square root of x over square root of x, if that's what you mean. But based
Okay,
on
miss.
that, based here on the choices, John, that you have to select your answer, you just have to, of course, select the best one. So this one, the C is wrong. This one is also wrong. This one is also wrong. So the answer is this. Okay, so the D.
Thank you, miss.
Okay, so I'll clear my markings now. So we go to the next. We have the next review here. What is the derivative of x? Actually, class, this is function of x. That's not x. So it's function of x equal to the square root of second x squared. So this is another application of chain rule. So anybody who can tell me the derivative of this f of x? That would be written as f prime of x. No raised hands here. No volunteer. So if you use chain rule, your second function is raised to an exponent of 1/2. So you can use power rule. So you have 1/2 times the second of x squared raised to negative 1/2. Because you subtract 1 from 1/2. Then you use chain rule here inside. So what's the derivative of the second? So it's second x squared tangent of x squared. Because the derivative of second theta is second theta tangent theta. So that's it. My theta is x squared, so I copied it. But then we have x squared here. It has a derivative of 2x. So I'm just placing it here, but it's supposed to be placed in here. So these 2 here and this 1/2 will cancel each other. And your f prime of x will be, you have this x here, x second of x squared tangent of x squared divided by, because this is second of x squared raised to negative 1/2. So it should be written here of x squared. Okay. Now what happens? The second of x squared is understood to be raised to 1. The second of x squared here is understood to be raised to negative 1/2. So negative 1/2 plus 1 is square root. So that is why you have here. You take this one out, you have still a remaining exponent here, which is 1/2. Because originally this is 1 minus 1/2, so that would be 1/2. So x square root of second x squared tangent of x squared. So that's our answer for number 3. That's using as well chain rule. Now, what about the 4th? Now, it's very important that you review the formulas that you have learned in differential calculus. That way, you can apply it later on as well when you do integration. Okay? The log of x cubed minus 2x to the base 4. So how do you get the function of x? Function of x prime, that is, because we want the derivative. So you have learned that derivative is prime, right? Second derivative is double prime. So that's the shortcut way of writing. Now, the derivative of a log function is the derivative of its argument first. So what is the argument? This one, log of u to the base a, for example. So we get the derivative of the u, and that is 3x squared minus 2. That's as per formula. Then we multiply it to the ln of the given base. It's automatic. You multiply it to the ln of the given base. Our base here is 4. So it should be multiplied by 4. And we divide it by the u itself. So the u itself is x cubed minus 2x. So that's the reason why you are seeing here D as the answer. du ln a over u. That's the derivative of log u to the base a as per formula. Now, we won't be able to answer this unless we recall the formula for that. So it's important that you review. Okay? Now, you are actually in a lot of an advantage because you are learning all these things online, and you can have your reference there. You can have your notes there beside you when you answer things. So as long as you have those notes with you and you have the correct formulas to use, you won't get lost. But if you still don't understand the way the formula works, those set of formulas that you have are useless. So any question here with the examples you're seeing? Yes, Richmond. Jem, Richmond.
Miss, I have a question though. So number 3, if it's cubed siya, miss, like for example, like square root of sec x cube, ano siya, miss? Like, is it considered as ma 1/3 gyapon?
Oh, correct. Ano no? You mean
I mean, sorry. The one, if
cube
it's
siya.
3, if it's cube.
If it's x cubed, then the derivative of that is 3x squared. You just change this, to 3x
Okay.
squared. The rest of the processes here are the same because
Same.
the x cubed here is the last thing that you will differentiate. So instead of writing 2x, because that's the derivative of x squared, that would then be for x cubed, 3x squared. That's how you learn it.
3x squared. Okay. Yes, miss. Thank you.
Sige. Question. Okay, so I'll clear my markings here. Now we proceed to the real thing, and that's your calculus, because what we have done in the first 30 minutes is just review. Now, the process of finding the integral of a given expression is actually the opposite of differentiation. If I may put it simply, the integral of a given expression is the antiderivative of a given function. So, integral is anti-differentiation. Okay? Integration is anti-differentiation, if I may say. So, what is that anti-differentiation that you're saying, Miss Ali? So, you could see here that if we differentiate f of x, which is x cubed, this is your derivative. If you differentiate x cubed plus 1, you still have the same derivative because the derivative of this constant one is 0. If you differentiate x cubed minus 1, you still have the same derivative. So you have 3x squared. So we say that f of x, which is x cubed plus c, where c could represent any constant. In this case here, your c is 0. Here, your c is 1. And in here, your c is negative 1. So we say that this function of x, which is x cubed plus c, is an antiderivative of this 3x squared. So meaning later, if you get the integral of this 3x squared, you will learn later in a few minutes, the answer will be x cubed plus c. The c will depend on the limit of your integration. But since in the first part of our subject, we don't have limits to our integral, we'll be dealing with an indefinite integral, then it's just a c. It's just a c. So again, this x cubed plus c, where c is any arbitrary constant, 0 included, is the antiderivative of this 3x squared, which is the derivative of all this. Okay? So anti-differentiation is the process of finding the antiderivative actually, or the process of integrating. Now, to make it even clearer, we go here. If you're given this expression, we call the function of x in this expression as the integrand. We use this symbol as denoting we are processing the function's integral. So we call it the integral sign. And this differential of x, or read as dx, is the variable of integration. This f of x plus c, the one equivalent to this x cubed plus c, is actually the answer to this given integral. Now, we say that this f of x plus c is the antiderivative of this integrand that you see here. So meaning, later on, when you process the integral of a given expression and you have already the answer, you can check your answer actually. How? You differentiate your answer. If the derivative of your answer is the given function here, we call the integrand, then the process of anti-differentiation, we call integration, is correct. If not, there's something wrong with what you are doing. So we call this the antiderivative. We call the process here integration. When you differentiate the antiderivative, you go back to the given function, which is here in your given integral. We call it the integrand, the given function of x. Okay? Now, you may wonder why you have this constant of integration. I mentioned a while ago that you don't have the limits of your integral here. So since you don't have yet the limits, we will have that in the latter part of midterm or in the early part of end term. Your answer always, when you do integration or anti-differentiation, will have the arbitrary constant of integration c. Okay? Once you have the limit already, the answer to a given integral is a real quantity, a real number. So you won't be answering in the form of an equation or a function, but rather you will have values, actual values. Okay? So the integral sign, this one, evolved from the Greek letter summation. And dx is the appendage associated with delta x. Delta meaning change, this triangle here. The integrand should be the same variable as the appendage. What does that mean? The variables that you see here in your function should be the same variable that is written in your appendage or in your differential. If this is x and this is y, then you will be what we call performing integration, in which you will consider this particular function of x all as constants. Why? Because your variable here in the appendage is not the same as the variable that appears in your integral. And they should be the same variables. Okay, so anti-differentiation and integration are two synonymous terms. They mean the same. Okay, now we go to the next. We go to the very simple formula. If we have a simple power formula in differential calculus wherein you subtract 1 from the exponent of your given function, and you place that particular exponent before the function, in here, in integral, it's the opposite. You don't subtract 1, but you add 1. You add 1. So let's see. Now, the simple power formula is given here below, but we'll start with the simplest of all the formulas integration that you know. I will try, class, to show this on slideshow so that it will be bigger. Let me know if you cannot see it. Okay. Can you see it?
No, wala, miss. Na full screen, miss.
Okay.
I
Why
think
did
na, ano, miss, like half. I mean, like, I'm gonna get miss, like, no full screen.
Okay. Sige. Sige. Okay, so we go to the first formula that you have there in integration. You integrate a constant. This k is a constant. The answer is simply kx plus c. When you integrate an appendage like this, you simply drop the d. So that would be an x. When you integrate a dv, you simply drop the d. So that would be a v. In this case here, since you have a constant k, you copy the constant. It's just like you write the constant before the integral and then drop the d here and then add c. So that would be your integral for this given k dx. So the integral is kx plus c. How do you know that this answer of yours is correct? You differentiate this one. Differentiate kx plus c. How do you get the derivative of a constant times x? It's the constant itself, right? The derivative of a constant is 0. So you know you're doing the right thing because when you differentiate your answer here, it will go back to your given integral. Now, you can see here the thing that I have discussed a while ago. So when you're given a function that is being multiplied to a constant k, you set aside the k or you place it before your integral and simply process the integral of the function after. So there should be a dx here. If you have several functions, or let's say you're getting the integral of a polynomial, what you do, you process each of the terms in your, you process rather the integral of your given expression term by term or piece by piece. So you get the integral of the function of x and you add to that the integral of the g of x. Okay, now what about this power formula? So it's actually the title to this, but before we discuss this one, of course, I need to discuss this because these are properties for you to know regarding how you integrate constants with variables and expressions which have several terms, so they are needed. So when you have a function raised to n, using the power formula requires you to simply add 1 to the n in your function. So you copy x raised to n, you add 1 to n, and the resulting exponent here to your function, that becomes the denominator. So you have x raised to n plus 1 over n plus 1 plus c. You cannot use this power formula, the simple power formula, if n is equal to -1. That will be discussed in the next meetings because it will be you'll be given a different formula to use. But in this case, all other n's, as long as n is any real number, can be processed using the simple power formula. Okay? What you have here on the left is just the differentiation equivalent of what was done here on the right side. Our main goal is the one that is written on the right side. So it's just simply showing you that if in your differentiation, you can differentiate piece by piece, you can do that in integral. If in differentiation, you can set aside a constant and differentiate the given function, you can also do that in the integral. Okay? Now, we go to this example that you have here below. Okay, I'd like to clear first the markings on top. So the integral of 3x dx, this x here is understood to have an exponent of 1. So what happened? You set aside the constant 3 and you process x dx. So that would be 3 times x raised to 1 plus 1. And this 1 plus 1 here is reflected in the denominator. So your integral is 3 halves. So 3 over 2 x squared plus c. That's using the very simple power formula. Okay? I think that's very clear. Okay, we go to the next. Now, you have -2t squared dt. You set aside 2 and you use power rule for t squared. So what is that? That would be 2t raised to 2 plus 1. The exponent here reflected in the denominator, which is 2 plus 1. So you have -2 over 3t cubed plus c. The same applies here. You could see here that this time you have x squared plus 3 quantity squared. Now, you have this raised to an exponent, and this is a squared binomial. So what will you do first? Since you have a variable that is raised to an exponent and it's being squared in here, you cannot use power rule because you can use power rule only in here if the derivative of this x squared is together with the dx. You can make this as your entire u raised to n, provided that you have the du, but we don't have. Your du for x squared plus 3 is 2x dx. You only have dx. So it cannot be done. So what you should do is expand. So please expand. So when you expand, you use your algebra. So x to the 4th plus 6x squared plus 9. Then now, since it's expanded, you can recall the things that I have discussed in the previous slide. Process the integral of this polynomial term by term. So you have x to the 4th dx. This one has a constant 6, so you place it before the integral. You have x squared dx, and that one you have 9 dx. Then you can use now power rule for each. So for this one, you have x to the 5th over 5. You add 1 to 4. And for this one, this would be, you have x cubed over 3. You have 6 here, so that would cancel with the 3, and that leaves you with the 2. So that is why you have 2x cubed. And that one is 9 dx. What did I say about integrating the appendage? You drop the d. So you simply have the x. So 9x, 9 multiplied to x. So this is already your integral. When you have something written in the denominator, you can always write it with a negative exponent. It's equivalent. So 1 over x cubed is x raised to -3. And you use the power rule just the same. So that would give you x raised to -2 over -2. Or since this is negative, you may place it in the denominator. So -1 over 2x squared. So the power rule is also applicable to fractional and negative exponents. So meaning whether your exponent is 3/2, 1/2, or -5, -2, power rule is still applicable. Any question? Okay, we go to the next. Now, we're done with power rule. We go to the simple trigonometric functions. And we start here with the, of course, the trigonometric functions. This you encountered first in your trigonometry in high school, and you have even an extended understanding of these trigonometric functions in your senior high school. So now we will go to the integrals of this standard trigonometric functions. So cosine has an integral of sine. Sine has an integral of negative cosine. Secant squared has the integral tangent. Cosecant squared has the integral of negative cotangent. Secant u tangent u has the integral of secant u. And cosecant u cotangent u has the integral negative cosecant u. What will happen if you will differentiate your answer here? It will go back to this. Derivative of sine, cosine. Derivative of negative cosine, positive sine. Derivative of tangent, secant squared. Derivative of negative cotangent u is cosecant squared u. Derivative of secant, secant u tangent u. Derivative of negative cosecant u is cosecant u cotangent u. So your answers when differentiated, these are your answers when differentiated, will go back to the integrand, the function that appears in your integrand. So that's the reason why we call integration is anti-differentiation. Okay, you have the differentiation formulas here, and you have its equivalent integral on the other side. Now, what does this, by the way, du implies? Sorry, du. Du means the derivative of your u. You can only place here sine of u when the derivative of your u here is being multiplied to this entire expression of the cosine u. What do I mean by that? For example, I write here cosine of x squared times 2x dx. This cosine of x squared is your cosine u. This your u being x squared. What's the du of that u? 2x dx. So I can answer for this sine of x squared. What will happen, Miss Ali, if I don't have this? For example, I only have dx. Can I still answer sine x squared? The answer is no, a big no. Why? Because as you can see here, your cosine u multiplied to the derivative of the u will give you the sine of u. If the derivative of the u here of your functions is not present with it, you cannot write these answers. You cannot write this right away as the answers. Maybe you need to do what we call substitution, or you need to manipulate first your given integral. That way, accompanying your trigonometric function, whatever is the trigonometric function, is the derivative of its argument. Miss Ali, what do you mean with the argument? The argument is the u or the theta of your trigonometric functions. If comparable to the name of a person, Juan Tamad, if I would just simply say Juan, there's so many Juan. But when I say Juan Tamad, Tamad being his family name, for example, then I'm referring to a particular person. So the same thing with these trigonometric functions. Without their arguments, it does not have any essence at all. Wala na siya pulos, wala man na siya naghatag identity sa iya. The thing that gives it identity is its argument. So remember, whenever you are given a formula for the integral, Remember that the du is to be always interpreted as the derivative of whatever is the u that is written in the formula. If that derivative is not complete, you have to make it complete. If it's not present, then the formula that is given to you is not applicable. Okay? I will proceed. We'll discuss samples of trigonometric expressions. I will decrease so you will see. Now, 3 cosine x, 2 sine x. Simple. Your arguments are just x, so the derivative is dx. So you can use right away the formula. You set aside the constants and you process the integral of the cosine and the sine. The cosine has an integral of positive sine. The sine has an integral of negative cosine. So giving you 3 sine x plus 2 cosine x plus c. For number 2, you have your 1 over sine x quantity squared. Now, this sign, you know, in your trigonometry, 1 over sine is cosecant. And this is good as an example because some student doesn't understand that whenever you have written something like this, it's equivalent to sine cube x. Whenever you have written 1 over tangent cube x, that's equivalent to writing, this is equivalent to writing as cotangent x raised to 3 or cotangent cube x. This 3 are the same. The reciprocal of the tangent and is the cotangent or vice versa. When you cube, when you raise to a particular power, let's say 3, a trigonometric expression, it's equivalent to writing it in this manner. Okay? So in this example, you could see that that's the case. A cosecant squared x, okay, a cosecant squared x has the answer negative cotangent x. Why? Because if you differentiate a cotangent, the answer is negative cosecant squared x. So it being negative, that makes it positive. This one that you see is a correction class. So that is why you see there as there's a horizontal line that is striking it out there. So the integral of 1 over sine x quantity squared is negative cotangent x. For tangent squared x, we don't have a formula for that. Let's go back to our formula. So you will see. We don't have a tangent squared x here. Or a tangent u du. Tangent squared u du. So what will you do? You will do this a lot in integral. Whenever a given trigonometric expression is not in the standard form or in a particular formula is applicable to, you think of a probable, you think of an equivalent identity that you can replace it with. That way, it's possible for you to integrate it. Now, you have in your trigonometry, this particular expression, cosine squared x plus sine squared x is equal to 1. Actually, it's the parent main identity. If you will divide this by cosine squared x, what will be the answer? You will have 1 plus sine squared over cosine squared is tangent squared x. 1 over cosine squared x is secant squared x. So you will replace the tangent squared x that you have here by its equivalent from this particular equation. So your tangent squared x is secant squared x minus 1. See here? Why will you do that? Why will I do that, Miss Ali? It's because you don't have the direct integral of this. So you have to find ways. That way you can still use the formula that were given to you. So with the second and the 1, of course, you can integrate. You just simply process this term by term. So you have secant squared x dx as your first integral. And then subtract from that the integral of dx. The integral of secant squared x is tangent x. The integral of dx is x. Let's see. So this is your answer. This is the answer for the given integral. You have any questions? Yes, Vincent, John.
Miss, for the example number 3, will the minus 1 be removed, Miss? Like sec squared x dx and minus. So the 1 isn't present, Miss.
Again. I did not get the question. You will
Uh,
remove
where did 1 go, Miss?
which one?
Uh, the
Which
number 1,
one?
Miss. At in example 3.
Number
Yes,
3?
Miss.
O diin nga 1 ang namin mo nga madula ini?
Yes, Miss.
No, it did not go anywhere. This cosine squared x was distributed to this 3. Cosine squared x divided by cosine squared x is 1. Sine squared x over cosine squared x is tangent squared x. 1 over cosine squared x is secant squared x. So it's not gone. What you did is you distributed the cosine squared here as a divisor for all this. This is a standard identity, by the way. Now you may wonder, why did I do that? Because I want a tangent squared, the one I have here. I want an equivalent expression for the tangent squared. The only way I can do that is if I divide this main identity that I can recall from my high school by cosine squared, because sine over cosine is tangent. Do you get it?
Okay, Miss. Thank you.
Okay. Some more questions? Okay, none? Sige. Let me check if I still have examples here. I will just end with the 4th and the 5th example. That way we can start with the other topics next week. Okay? Example 4. It's still on the application of the formulas we discussed. So you have a rational expression. When you say rational, it's a fraction. It has a numerator and a denominator. Whenever you see one, of course, it's expected that students will right away be, shall I say, they will think, oh my, this is very difficult. Why is it like this? The first thing you do is, of course, stay calm and simplify the given expression. How will you simplify a fraction? You simply divide the numerator by the denominator. So you can divide the numerator by this, the first term, and then divide the denominator by this. So as a consequence of that, why do you have a cotangent x here and a cosecant squared x dx? Let's say I'll write here what should be the answer. So you have the integral of, I'll have a 3. I'll process this one first. So you have cosine cube x over sine squared x cosine squared x. Okay. First integral for now. We'll do the first integral for now. Now, if you will have this cosine, I'll use a different ink so you will see the difference. If I'll take this out, I still have 1 remaining here, right? That cosine here, that 1 cosine, and together with the sine in here, that's your cotangent x. But remember, you only have cosine x over sine x for the cotangent. Where is the other sine? Your 1 over sine x is this cosecant x. So this first term, the original that you have, is equivalent to this when simplified. Now you do the same for the second term. So your second term is 4 integral of, so you have sine cube x over, same thing, sine squared x cosine squared x. Now I'll use a different color so you will see. This sine squared and the sine cube, of course, will cancel. But you still have 1 left here. The sine over 1 of the cosine here in the denominator is your tangent. So you already have a sine x over cosine x. Direya may bilin ka pa nga 1 over sine x. Direya ang bilin mo 1 over cosine x. What is this 1 over cosine x? That's your second x. Do you follow? So you simplify a complex rational expression this way. Now you could see that cotangent cosecant is actually negative cosecant x and tangent secant is positive secant x. It's part of the formulas that I have shown to you a while ago. Cosecant cotangent gives you a negative cosecant, a second tangent gives you a secant. So this one now can be integrated, where the original that was given to you cannot be integrated. If you will allow me to clear my markings, you don't have any questions. If I clear my markings, this one, and this one here that you're seeing is actually here. Here. Second tangent, cosecant, cotangent. Here's the answer. So that's the one. Okay? Now, the last part here is when you have a 1 over 1 minus cosine x dx. Now, I would like to borrow probably 3 more minutes. Whenever you see, class, a denominator, which is 1 minus a particular trigonometric expression, sine man ini siya abi, cosine man ini siya abi, you multiply it by an equivalent expression to 1. This is 1 plus cosine x over 1 plus cosine x, which is a conjugate of the denominator. Now, you will ask, Miss Ali, what do you mean by conjugate of the denominator? Your denominator has two terms. The negative of the second term makes it a conjugate of the original. So what is the conjugate of this? It's 1 plus cosine x. But we are not allowed to simply multiply 1 over 1 plus cosine x because that will alter your original integral. You are only allowed to multiply by 1. And this one is 1 because they're just the same. So if you multiply the original integral by 1 plus cosine x over 1 plus cosine x, it will give you this. Right? 1 minus cosine x plus 1 plus cosine x, according to your algebra, will be this. 1 minus cosine squared x is sine squared x coming from your trigonometric identity that I've showed to you a while ago. Now, with this, just like what you have done here, you distribute the sine squared x as a denominator to your 1 and your cosine x in the numerator. 1 and cosine x. Now, this one, the 1 over sine squared x is cosecant squared x, which has an integral which is negative cotangent x. It's here. Here. Okay? So that's it. While this one, your cosine over sine, for the second term, this cosine over sine times 1 over sine x, ini siya ho, equivalent man sa sini, is actually the integral of cosine over sine is cotangent and 1 over sine x is cosecant x. Your cotangent x, cosecant x is actually negative cosecant x. Again, coming from the set of formulas we have here, cosecant cotangent is negative cosecant x. So you have it here. So you see how important is differentiation to integration? Why? Because integration is complex in itself if you do not know how to differentiate. So it's really important that you know the derivative of one. That way you'll be able to check later if your answers are correct. So this is our answer for our given integral, which is this one. Okay? What you have learned so far is just the tip of the iceberg. Why? Because these are just but the fundamental formulas. You are not yet taught the techniques. The techniques simplify the given integral expression. That way you are able to apply the formulas that were given to you. So we'll stop here for now. We will continue this next week. Hopefully we can finish this one and continue with the next. So I have placed your problem set in Canvas. Those that you can answer already, please do. Ang hindi pa ma-answer, kaya wala ta pa ma-discuss. Siyempre, hindi nyo pag-answeran. Do you have any question? Any question?
None, miss.
I'll stop sharing.
None, miss.
Okay, I'll stop sharing. Can you please, there's only 19 or 18 of you. Can you please give me a reaction if you're physically present there? I'm checking the attendance. I'm getting a screenshot. Ryan Joshua, are you there? Okay, so you're there. So I'll take a screenshot now because everybody is here. I don't have the class list because, wait, Renan, wait. Because okay, yes, Renan, you're raising your hand.